An important property of a voting system is that every vote is correctly counted and left unchanged after being cast. No modification, no deletion, no funny business. This is data skeptic consensus, the 13th installment in our series about how multi-agent systems achieve collective decision-making. Today on the show, I speak with Niclas Boehmer about his research into the robustness of elections. A number of interesting combinatorial problems arise as we discuss how to model bribery and vote modification mathematically. How many altered votes would it take to sway an election?
My name is Niclas Boehmer. I'm a second-year PhD student from TU Berlin in Germany, where I'm part of the research group Algorithmics and Computational Complexity, led by Professor Rolf Niedermeyer.
Well, thank you so much for coming on the show. Could you tell us a little bit more about your PhD work? What specific areas in complexity are you focused on?
So I'm mostly working on questions from the area of collective decision-making. And collective decision-making is some umbrella term for different settings or scenarios where a group of agents come together and have different and maybe conflicting opinions about alternatives, and where we want to kind of find a compromise alternative or an alternative that makes everyone happy to a, let's say, fair extent. And I analyze questions from this area from mostly, as you already said, a complexity, theoretical, and algorithmic point of view.
I'm aware that there are some aspects of multi-agent systems that frame it in a game theoretic context or maybe decision theoretic approaches. Does that overlap or is that separate from your interest?
So we are not really doing work, let's say, closely related to classical multi-agent systems. But interestingly, kind of the work that I'm doing in this collective decision theory field is somehow became a subfield of multi-agent system. At least if you look at the conferences where we usually publish at multi-agent system conferences. And multi-agent system is somehow always an application which we have in mind. So a lot of these collective decision-making scenarios also happen classically in some multi-agent systems.
So some of this is well highlighted in the main paper I wanted to invite you on to discuss, which is titled On the Robustness of Winners, Counting Briberies in Elections. A lot of things to unpack there. I guess maybe this was the first time I ever had a bribery formalized in a mathematical way. So could we start with that? How do we quantify bribery?
So when it comes to elections, bribery is kind of a pretty natural and also quite well understood problem. And what we aim here for is, or the model that we have in mind is, we have an election and we have a briber who wants to achieve a certain goal. In the context of an election, it's usually making someone win the election or preventing someone from winning the election. So this is the goal that the briber has, and the briber knows kind of the original election. And then we give the briber typically a given budget. So let's say he's allowed to delete 10 votes. And then the computational question that we have in mind is it possible for the briber to pick like 10 of the votes in the election smartly and to delete them such that he achieves his goal, for example, making a certain candidate win the election?
Gotcha. So we've just finished up an election in my country here in the U.S. There was a Republican and a Democrat who were running and many other people. If you were, very resourced and could manipulate the elections, maybe you could have pulled it towards one of the two major party winners. But if you had done enough manipulation that a third party won, that would have been quite unprecedented by our country's standards. How do we measure that distance that I feel like it's intuitively there? How can we quantify something like that?
So if you have this computational question I told you about in mind, then you can also obviously ask for the minimum number of operations that the briber needs. So if you have, again, my election, I have my goal. And then the question is now, how much budget do I need? How many votes do I need to be able to add, or do I need to be able to delete to realize my goal? And if you do this for every candidate separately, you will get for every candidate a number. I mean, for the initially winning candidate, the number will be 0 because you don't have to change anything. For all the other candidates, it will be probably not 0 because they are not initially winning. And thereby you also somehow discover a ranking of the candidates. So this gives you a feeling for how far away someone is from winning or losing the election with respect to the operations that you allowed. So for example, deleting or adding votes or somehow modifying the votes that you already have.
Well, let's talk a little bit about the voting mechanics. The paper covers two different ways that people might vote, plurality and border voting. Could you go into how those systems operate and maybe in the context of those, how this manipulation takes place?
So the two voting mechanisms we cover, plurality and border, are both a special case of so-called scoring-based voting rules. And the idea here in scoring-based voting rules is that every voter is allowed to give points to candidates. And in the end, the candidate with the highest sum number of points wins the election. And for example, in plurality, I'm allowed to give 1 point to my most preferred candidate. So it's pretty simple. It's also typically how ballots are casted. You simply mark your most preferred candidate and thereby he gets a point from your vote. Border is a little bit more tricky. By border, or in the border election, we take the preference relation or the rankings, how the voters rank the candidates as an input. And then we award, if we have M candidates, we award M-1 points to the first candidate, to the most preferred candidate, M-2 points to the second most preferred candidate, M-3 points to the third most preferred candidate, and so on. And as I said, we accumulate the points given to the voters by the candidates, and then in the end, the candidate with the highest score simply wins. And in context of bribery, for example, you have the operations. The power of the operations differs a little bit which voting rule you use. So, for example, for plurality, it's only kind of crucial to who is your most preferred candidate. So only this is important. So, for example, if you say a briber, you are not allowed to touch the most preferred candidate of a voter. You cannot simply convince people to change their most preferred candidate. Then simply bribing is impossible in a plurality election, whereas in a border election, like every rank of a candidate matters. The exact ranking matters and not only the first candidate.
Gotcha. Yeah, I have to confess, I would never sell my vote to anyone. That just seems offensive. But if I was voting with border system, and there would come a point where I wouldn't much prefer candidate 18 versus 19, and if someone said, hey, I'll put $5 on you swapping those two, I guess that would put my ethics a little bit in question. I'd have to think about it, right? Is that the concern, that with a wide range of candidates, just the sheer volume could make the opportunity for things like this to fall in?
Yes, exactly. And this is somehow maybe also one of the main disadvantages of the classical border rule, because, I mean, there are two sides to it. First of all, it's easier maybe to convince people of changing their rankings of not so preferred candidates, but maybe you are not even able to rank them. And if we require that you really submit a strict ranking where it's really putting all the candidates after each other, but let's say between or after your top 10, you basically don't really care anymore and all of them look pretty indifferent to you, and you then just rank them arbitrarily. I mean, you obviously award to some of them quite a high number of points then, and to some of them quite a low number of points. So maybe by doing this, you make some candidate win, but you didn't really actually care about them at all. And this is somehow the main problem with such rules that really take into account the full votes of voters.
And the title has this interesting word robust, which I understand pretty well in the context of writing software or developing an algorithm that's robust. This is my first encounter with it in an election, but it actually suits us quite well. What is it to have the property of robustness in one's election?
Maybe I should start with explaining what I mean with robust in the general context. So if we have a computational problem, or we have just, let's say we have some input and we want to find a solution for some whatsoever problem, then the robustness somehow captures how resistant my solution is to change in the input. So if I have a solution, and this is the solution to a certain input, and then I shake the input a little bit up, for example, in context of election, by deleting votes, by adding votes, and then robustness tries to capture how likely it is that the solution that I initially kind of came up with remains to be a solution also after these changes happen. And yeah, so in the election context, it's about we are mainly interested, as we already stated in the title, kind of in the robustness of the election winner. So if we have an election, we know our winner. And now the question is, okay, maybe the election will change a little bit in the future, or the preferences of voters will change a little bit in the future. For example, some of them may disappear, or others will come in, or some of them will slightly change their preferences. How likely after this change happened is it that the initially winning candidate also is a winning candidate in the changed election?
Yeah, that makes a lot of sense. If I'm able to manipulate the election, I mean, that's wrong. I shouldn't be allowed to change other people's votes, but if I can't sway the overall election, then my nefarious efforts are in vain.
Yes. So this would be an example if you have a really robust candidate that also wins no matter what you do. Obviously, also only if you have like a given budget. I mean, if you can change everything, it's like boring. But if you have a really robust candidate, this can really somehow prevent you from even trying such things.
Thanks to this week's sponsor, Springboard School of Data. Did you know data science is a fast-growing career field with 650% growth in jobs since 2012 and a median salary of $125K? Springboard has identified that data careers are going to shape the future and has responded to that need by creating the Springboard School of Data, a comprehensive end-to-end data career program that encompasses data science, data analytics, data engineering, and machine learning. Each Springboard course is 100% online and remote, and each course curriculum is tailored to fit the schedule of working professionals. Every Springboard student graduates with a portfolio of projects to showcase their skills to potential employees. All of Springboard's data courses are supported by a vast network of industry expert mentors. Springboard's tuition-back guarantee allows students to secure the role of their dreams and invest in themselves without risk. Want to learn more? Springboard is exclusively offering up to 20 scholarships of $500 to listeners of Data Skeptic. Simply go to springboard.com/dataskeptic for more information. So we quickly get into some combinatorics and these sorts of issues as you work out the mathematics. So I guess we're counting things. Is that the main approach, that we have to look and basically explore every possible swap that an adversary could make?
Yes, exactly. And what we are here particularly interested in is to measure for each candidate the probability of winning after performing some given number of swaps arbitrarily. So we also then say that we have an election at a given swap distance of some other elections. So it's always like we think of, okay, we have this case swaps that may happen or may not happen, but they could happen. And we perform them simply arbitrarily. We somehow want to have for each candidate the probability of the candidate winning after these swaps have been performed. And to calculate the probability, we actually have to count. And what we need to count is, okay, we have to look at all possibilities, or this would be the trivial approach, to look at all possibilities how to perform these case swaps. So to look at all the resulting elections and for all of them compute the election winner and then simply count, okay, we have for 100 of them, candidate A wins, for 200 of them, candidate B wins. And then by dividing for each of the candidates this number by the total number of elections at this swap distance, we get the probability that we are kind of ultimately interested in.
And is there no efficient way we can do this? If I have to count every possible election with, all these swaps, that's going to take me quite a bit of time. Is there no clever formula we could use?
Unfortunately, not really. So this is somehow what we were interested in the first part of the project or the paper, in somehow trying to either come up with efficient algorithms to compute this or to prove that it's not possible to come up with efficient algorithms because under some standard complexity theoretical assumptions. And we managed to prove for most of the questions that they are pretty hard. We were also able to identify some special cases. So for example, if the number of voters is small, then it can be done a little bit faster. And then we have special algorithms for this case of a small number of voters. But in generally, this problem is pretty hard if you really want to calculate this exactly, and especially that there does not unfortunately exist a formula. And that's why in the second part, where we really wanted to look at how these probabilities look like in elections that we generated or that other people generated, we relied to sampling. So we simply, and this actually one can do efficiently, we simply sampled some elections at some given swap distance of an initial election. And then for the sampled election, we looked, or the set of sampled elections, we looked how the probabilities of winning distributed there. So we calculated for each candidate the probability of winning in this set of sampled elections. And thereby one can obtain a quite correct, not really correct, but still still roughly in the range of the exact probabilities.
Is that a formal, like, upper or lower bound? Can you tell me it's within epsilon something, or is it just in practice it seems to work out?
So there are also some bounds, but they usually require a little bit more computational effort and a little bit more sampled elections than we were willing to do. So, the short answer is there are bounds where you can exactly say, okay, we know that after we sample, let's say 1 million elections, it's clear that with a probability of 99%, we are within like an epsilon of 1% of the true results. But this was computational too expensive for us in our case. And that's why we simply looked at, for smaller numbers, we calculated the probabilities exactly. And then we looked how sampling or how much samples we need to approximate them good enough for our purposes.
Interesting. Yeah. What sort of convergence did you see in that case?
What do you mean by convergence?
As your sample size increased, there would be a point of diminishing returns. Maybe you could say something like, after roughly 100 samples, we're having, very close to the correct result. Maybe it varies by the simulation. I'm not sure.
Okay, so I think that we noticed that this depends on the size of the election. So it depends on the number of voters, it depends on the number of candidates, and it also depends on the number of, the swap distance we want to look at. For example, at small swap distance, you simply don't have that many different elections that lie there. But we, in the end, somehow settled to using roughly 10,000 elections for each swap distance we examined. So somehow in our experiments, we noticed that even at a pretty large swap distance where we have quite some elections lying there, 10,000 were usually enough to get a pretty good picture of the precise results.
This swap distance metric is very interesting to me, and regardless of the outcome, I think people would hope to have a wide swap distance. In other words, we'd like elections to be kind of obvious, right? If we're too spread apart, there'd be less confidence in a leader. It would be, in some way, to me, more pleasing to find out that a winner of any election won by a significant margin, and this was a value we optimize. Is that part of the intent, or is there some kind of a motivation in that direction, or do you use this metric in other ways?
So the metric of looking at the swap distance can be kind of motivated in two different ways, at least from our perspective. The first one is the good capture for noise. So as you said before, if we assume that maybe people don't really care about how they rank candidates in the end, then they make some accidental swaps there. Or if they are not really informed about they don't have certain information, then they maybe misrank two candidates. And if this happens multiple times, then they perform multiple swaps. And swap distance is simply a handy way to measure this noise in the data, but also to somehow measure future change that may happen. So, humans tend to change their mind quite quickly. And there it's somehow reasonable to assume if I have my vote now and I have my vote in the future, then the swap distance between should be relatively small. So it should be possible to transfer my new vote, my new opinions, only using a few number of swaps, because if this wouldn't be possible, then this means that I change of my mind fundamentally, which is not so likely in practical situations, I would say.
And I know this is sort of a curveball question, but I'm just curious, maybe not for a governmental election, but perhaps, a company or an organization of some kind. Do you think there's any good motivation why an organization like that might consider adopting some policy? Like if a leader doesn't have a wide enough margin or swap region separating them from the other candidates, that their term is shortened or something clever like that? I don't know.
Yeah, so this is actually what our kind of our dream would be, let's say. So we tried here in this paper to somehow develop a framework, how one get a feeling for how close elections are, how robust winners are, how high their probabilities are also if we change the election by a bit. And we somehow, using this framework, I think it's pretty easy, or at least we hope that it's easier to identify elections which are maybe a little closer than they seem to be. And especially depending on the context where people or decision makers may even reconsider to re-examine the election issue, to maybe ask the voters, okay, please think about your votes. Are you really sure that this is your vote? Or to also give them additional information to make them listen to experts, or I don't know, or even maybe in some contexts, if you have, for example, experts voting on a proposal for some funding, to maybe ask additional experts to also give their votes to somehow increase this margin ultimately, and then be really sure about the election winner that you find and that you kind of name and gets funding in this example.
I'd love to unpack some of the experiments that were done as part of the work as well. One of the things that's most fascinating to me is some of the dynamics you guys observed as you explored, well, what if there was someone who had this amount of swaps they can do and that sort of thing? I guess to get us going, broadly speaking, what were some of the results you were hoping to find when you set out to do the experiments?
So first of all, we somehow wanted to get a feeling for how the probability of initially winning candidate behaves if we make more and more random swaps. So, initially the candidate for like 0 swaps, it's clear we have the initial winner has 100% probability of winning. But then if we start to make a few swaps, let's say like 10 or 20 or 30 arbitrary swaps, so completely at random, then we were interested in seeing how much or how fast this probability of winning declines. So for example, even after performing, let's say 10 arbitrary swaps, could it be that the initially winning candidate, which is at 0 swap distance 100% probability of winning, only has maybe a probability of winning of 40%? Already after performing these 10 few swaps here. So this was kind of our general motivation, that we wanted to first of all look at how fast this probability can go down, so how unrobust winners can be and how often this happens in practice. And for some of the elections, we looked at this really happened quite quickly. So there was one example of an election where we had like an initially winning candidate, and then we looked at performing half a swap. So, for every second voter, we performed an arbitrary swap in his vote. And if we did this, the probability of the initially winning candidate winning the election dropped below, I think, 40% or something like this. And there was another candidate which, even after just doing these few random swaps, like his probability increased from 0, because initially he was not winning, to, I think it was like 58% or something like this. So it can really flip pretty fast. And there are two things that you have to remember here. First of all, it's not that we came up with random arbitrary elections. It's always possible to find special cases where such things can happen quickly. But this was actually like an election generated using a quite of well-known and also by experts approved models. And the second thing here, we are not looking at making the swaps on purpose. It's really about arbitrary swaps. So it's not about we make the swaps exactly in a way such that our initially winning candidate loses points and the other candidate we want to make the winner gains points, but it's really about making arbitrary swaps. And even with half an arbitrary swap per vote, we sometimes observe this behavior of a significant decrease in the probability of winning.
That seems kind of surprising to me for some reason. Maybe it has to do with the sample size, and I missed that. What is the population of the experiment?
We did multiple experiments. For the largest one, we had 100 voters and 10 candidates. So like one swap per vote is not a lot, but it's also not nothing.
Gotcha. Yeah, but it's still quite a shocking result, I guess, even for that size of population, that so many untargeted swaps could reduce the probability of the win. I'm guessing you just kind of randomly sample. Could you tell me a little bit about that mechanism you were mentioning that other researchers have already validated? How do you generate a random election?
This is its own research area, let's say. So there exist a bunch of different models. Maybe the easiest one is the so-called, or maybe the most plausible one is the so-called impartial culture model. And what we do here is, we have all possible votes. In our context, it's always all possibilities how to rank the candidates. And then we simply draw one after each other a vote from this pool. And if we draw a vote, we always return it. So it's really like every voter just has an arbitrary preference relation over the candidates. But actually, this is maybe not so realistic, because in reality, it's not as if like people would really randomly vote, randomly rank candidates, but there is usually some structure, because maybe there is some candidate which is objectively the best one or something like this. And this is captured by other models. So for example, there's a so-called Maloff's model, which assumes that there is a reference ranking, so somehow the true ranking, and then the probability of sampling a vote depends on the distance of the vote from this true ranking, so for the given reference ranking. And maybe a third interesting model that is also a little bit more visual is a method where we assume that candidates and voters are points in the space. So let's say just in 2 dimensions. So what we do here is we sample, or we arbitrarily put voters on some 2-dimensional space, and then we arbitrarily put candidates on this 2-dimensional space. And then the ranking of a voter, or a voter ranks candidates by their distance. So we simply measure the distance between the points, so the distance between the point of the voter and the points of the candidates, and we put the closest candidate as our most preferred candidate and the candidate furthest away as our least preferred candidate.
Thanks to this week's sponsor, Nordvpn. Everyone needs to protect their home internet connection, and Nordvpn is one of the best choices out there with super fast servers in 59 countries. You can unlock Netflix and your favorite entertainment websites, protect your data at home and while traveling. There's absolutely no data logging, 24/7 customer support, 6 simultaneous connections supported, and with a 30-day money-back guarantee. How can you not want to give this a shot? NordVPN is compatible with Windows, Mac OS, Linux, iOS, and Android. Basically everything. And that's with unlimited bandwidth. NordVPN has an extension for the Chrome browser that is lightweight, user-friendly, and super secure. That makes this totally easy. And for data skeptic listeners, NordVPN is offering a special Black Friday deal. With every purchase of a 2-year plan, you will get 4 additional months for free. Go to nordvpn.com/dataskeptic and use our coupon code DataSkeptic at checkout. Let's talk a little bit about some of the complexity theory aspects of this. I see some very hairy classes like NP-complete and Sharp-P-hard in here. These are hard algorithms to run and seem practically infeasible. You did mention that you're getting pretty good approximation results, but if we tried to scale this up even beyond the experiments you ran, do you think those approximations would hold? Or do the complexity classes you're facing here make this even approximately intractable?
That's a pretty good and valid question. I think so from my feeling first of all, we did not show any theoretical inapproximability results. So there might well exist some algorithms that are able even to guarantee some approximation, but this was not the direction we investigated, let's say. But like really looking at the sampling-based approach, I think that if you exercise some caution in how you write your algorithm and put a little bit more effort into this compared to what we did, and it's probably also feasible for a higher number of candidates and voters, but it's probably not so much feasible for like really large scale elections like a presidential election. I mean, this would be probably completely out of scope. But in settings like this, you can also somehow take a step back and redesign your approach. So if you, for example, have the presidential election or like really large elections, it's quite likely that the votes will be quite similar, if not even identical. And if you, for example, have a lot of identical votes, then things become again a little easier and you can somehow use a different sampling approach. But in general, we don't have an efficient algorithm to do this, not even for smaller-ish elections like the ones that we looked at.
And do you have any, on the more like softer science side, any takeaways from this work? Are there ways in which, or maybe bits of wisdom that could be extracted here to help guide, not necessarily presidential elections, although that's fine too, but what if I start some little charitable group and we need ways of making decisions? What are some of the insights that you might take away if you were starting something new?
So first of all, collect full preferences, because this is also somehow our curse a little bit. And this is that for most elections, most intuitively, people use plurality. So they simply give 1 point to their most preferred candidate. And this usually also has as a consequence that people only list their most preferred candidate. If this is the only thing that matters, people only will think about this one choice. But this makes experiments and like analysis like we did completely impossible to carry out, because we heavily rely on that we know the full preferences, or at least like some important parts of the preferences of voters. So if you really want to look at robustness of winners, the first thing that you have to do is to ask voters to really rank all candidates, not only their top 1 and maybe even a little bit more than their top 5. And if you then do this, then you can somehow try to look at our approach and to measure the robustness, to measure the probability of candidates winning the election, even if some swaps happen. And you might, in certain situations, find out something interesting and might find out something that makes you wonder whether you really selected the right one as the winner, or whether you to simply exercise a little bit more caution in designing and performing the election.
There's one mathematical idea I'm going to guess you've bumped into, even though it's not totally related, and that's Arrow's Impossibility Theorem that I'm actually going to do a future show on. But I'm guessing you maybe have some familiarity with it, and it's about the kind of a paradox of, voting systems and how we get one that has all the properties we'd like. Do you see that this aligns anywhere there? Are there aspects of which, maybe we stick to plurality just because it's simple and people don't have to know that many candidates? Are there any kind of results here about a cautionary tale, perhaps?
It's actually a good question. I think that our work can somehow add or has the potential to add a new perspective. So usually, and this is also what Arrow's Impossibility Theorem, as you said, is about, we have a bunch of properties that voting rules can fulfill. I think there's even a Wikipedia entry which lists 30 or 50 properties that voting rules can fulfill. And Arrow's Impossibility Theorem says, for example, that a certain natural subset of these properties cannot be fulfilled together. Or that there cannot exist a voting rule fulfilling all of them. And what we can add to this picture is that we can bring in the perspective of robustness. And what this means is that we can, in our experiments, we also saw, for example, that if we use plurality, winners are far less robust compared to if we use border. So if we take into account, as I said, with border, the full preferences, then the outcome, the winning candidate, is likely to be way more robust if compared to just looking at the plurality winner. One can come up with examples where this becomes pretty obvious. So, for example, if we have an election where we have one guy ranked first in 50% of the votes, but he's ranked last in all of the other votes. And then we have a second guy who's ranked first in 49% of the votes and ranked second in all the remaining votes, then it will be quite likely that if we make a few random swaps, this 49% candidate will actually gain some points and there will become the winner of the election. Whereas if we would have used border, then border would have detected this and already declared this second candidate as the initial winner of the election, even in the absence of any swaps.
Usually at this point, before I start to wind down the interview, I like to ask, is there anything you think I should have asked about that I didn't get to?
So I think one interesting point that I could make is about the score differences. So the scoring rules I talked about, they also give you an intuition about the margin of victory and the robustness, because in the end we have points for each candidate. And if you somehow just look at the difference between the winning candidate and the runner-up, this is already somehow an estimate how robust the winner is. And we discovered that our approach, this probability approach and the probability of winning at small swap distance, is somehow a little bit disconnected. So there exist elections where the score difference of two candidates is pretty small, but actually it takes quite some arbitrary swaps to really turn the election around. And there also exist elections where it's completely the other way around, where you have a small score difference of candidates, and this somehow is also reflected. If you perform just 10 swaps, then the picture completely flips.
Oh, this is very interesting because normally when there's a close election, it's kind of looked, at least in my mind, unfavorably upon because, hey, even if there could have been a couple of fraudulent voters and they could have swayed it, it's such a small margin, maybe we need a recount. But you're telling me actually that's not the complete picture, that the winner might actually have a stronger win, just not counted that way. Does that apply to our plurality voting too, or just the board accounting?
Yeah, it also applies to plurality.
Oh, very interesting. So this is a metric that could be very informative about the margin of wins, the true margin of wins, I guess.
Yes, and this is also somehow what was our main surprising result that we took away from the experiments, because this was not really what we initially expected, let's say. So we somehow expected that there will be a disconnect, or that maybe things will not be exactly reflected in the score, that the metrics will not completely be the same. I mean, this is usually or typically the case, but we were kind of surprised by the gap and also by some of the concrete elections which we found. So there were some examples where, for plurality, we had some examples where election winners, which were only ahead by, let's say, 3 points, were more robust in their election than election winners an election winner in another election who had actually a lead of, let's say, 15 points. So even if you have a lot higher lead in the score difference, this doesn't necessarily imply that you are also a more robust winner with respect to performing arbitrary swaps.
So given the applicability, it would be great if we could take measurements like this. But of course, we're going to have to face the computational challenges you've highlighted. With that in mind, what's next in this line of work? Where do you see things going in the future?
So So first of all, it's possible or plan to also look at other voting systems. I mean, probability and border are maybe at least in our field, the two classical ones, also maybe the two simplest ones in some way. But there are also other voting mechanisms where we think that this disconnect in the scores or of the scores and our picture, our perspective may even become a little bit more profound. Also because some voting rules don't have such a high score range. So this means that some of them, in the case, if we have 10 candidates, only in the end, the candidates only have points between 0 and 9. And here it's way more obvious that we can really add a new perspective to the analysis of election outcomes for such voting rules. So this could be, or this will be kind of the first point. And the second point is we only looked at the robustness of winners with respect to arbitrary swaps in the preferences. But obviously, there are also other possibilities how you can modify an election. For example, one could look at restricting the swaps only to happen at the tail of the preferences. So as you already said, it's maybe way more likely that I make some swaps in the end. So that maybe I did some mistakes when ranking my least preferred candidates. So one could focus really on doing unified experiments that take into account these kind of real world dynamics. But one could also look at what happens to the robustness of winners when we consider adding and deleting votes. Some other researchers and also one co-author of mine already did this from a theoretical point of view, but they didn't do it from an experimental point of view. So the experiments that we did could be simply rerun, but now instead of looking at how robust someone is with respect to arbitrary swaps, we could look at how robust someone wins the election with respect to arbitrary deletion and addition of voters.
Interesting. Will you expect fairly different dynamics or similar concepts, if you had to guess?
That's a pretty good question. I'm actually not so sure about this, to be honest. I kind of suspect that it will be a little bit more connected. So I think that the score differences will be a little bit closer to what we will find out about the robustness of winners when looking at this addition and deletion approach. But I'm actually not so sure to what extent this holds. So I'm not really sure about the precise margins here. So whether, for example, performing 10% of all possible swaps is more powerful than deleting 10% of the votes. So that's really something interesting, and I think something that may also offer at least again a new perspective on how you can assess an election, and also stems from, so also has quite a little bit different narrative and a different motivation. So I mean, adding and deleting votes is somehow more in scenarios where you think that people will maybe decide on election day that they don't want to vote, instead of switching, making just small changes in their preferences, as we suggested or as we assumed that in our work.
Yeah, makes sense. Well, very interesting. I look forward to seeing how that goes. Niclas, this has been great. Thank you so much for taking the time to come on and share your expertise. Is there anywhere people can follow you online?
I have a webpage, which is part of the webpage of our great research group, Algorithmics and Computational Complexity at TU Berlin. So if you're interested in more works like this, then maybe this is the right point where you can check us out.
I'll have a link to that site in the show notes so people can check it out. Niclas, thanks again for coming on.
Thanks for the invitation.
That concludes this installment of Data Skeptic Consensus. Our guest today was Niclas Boehmer. Our theme song is Paradox by Odling. Claudia Armbruster is our associate producer. Vanessa Burciaga does guest coordination. And I've been your host, Kyle Polich.